Okay, welcome everyone to this week's AI seminar. Today, we're very happy to have Professor Junjie Hu from UW Medicine. So Junjie is an assistant professor in the computer science department and also biostatistics department at UW Medicine. He obtained his PhD from the School of Computer Science at CMU, where he worked with Graham Newbigg and Jamie Carbonell. So Junjie has done a lot of great works in particularly multilingual NLP, transfer learning, and knowledge representation learning. So one very famous work, most of the people who works in multilingual NLP must know is the extreme benchmark, which is actually Junjie's work. So today he is going to present about cross-lingual learning of named entities.
Yep. Thank you. Yeah, let me share my screen. Thanks, Muhal, for the introduction. Can everyone see my screen properly?
Yes.
Okay. Yeah. I'm very excited to talk about my research on multilingual NLP, and especially we will focus on name entity, cross-lingual learning of name entities. So as we know that many successful NLP systems have been developed to support communication in our life, such as machine translation system, personal assistant, and so on and so forth. However, as most of the existing NLP research predominantly focusing on English, partially because English has the most speaker in the world, and the figure on the right shows the top 4 languages with the most speaker. But we know that in reality, we have more than 7,000 languages that cover 240 language families. And all these languages have very different written script and cover a wide range of information across different topics, such as medical or financial topics. And in fact, if we divide the 7,000 languages by region, European languages only occupy about 4% of the languages, and native English speaker only makes up 5% of the world's population. More importantly, 82% of the world's population don't speak English at all. And I believe that the advances of language technology should not be the privilege of people speaking well-represented languages, and language technologies should be democratized to serve a broader population. And when we talk about democratize these language technologies, we need to first take a look at the underlying techniques that make the breakthrough of existing NLP systems. And over the last decade, we know that deep learning method is really powerful, but they rely on a lot of supervised machine learning data to train this neural network model. And in order to let the deep learning method to succeed, we need to collect large number of labeled data and train the model to mimic the human prediction. However, not all the languages have large amounts of labeled data because it's sometimes hard to find native speaker, and it's also take time for this speaker to understand the NLP task and then label the data. Moreover, when these multilingual problems are deployed to real-world challenges, the problem becomes much difficult because this application has much more complicated unlabeled data. And first, it's infeasible to annotate all data under different situations. And secondly, also requires a lot of domain knowledge to label this language data. And as we are working on cutting edge of scientific discovery, we all eager to make it easier for people to use these multilingual techniques and then address the challenging problems facing our society today. So first of all, let me give you a concrete NLP task as an example. Let's say if a person is given an article and then asks a question in Chinese, what diseases did antibiotics eliminate? Then the machine might not know Chinese, especially on some domain-specific name entities. So we ask a question, can we generalize a machine to understand all human languages? In the following, I will also show you another example of question answering task to illustrate the performance gap. The y-axis shows the F1 score of predicting the correct answer from a given paragraph. And at the very beginning, people use handcrafted feature and logistic regression to actually tackle this task. And later on, people use supervised method. And then most recently, people use unsupervised pre-training that even push the performance a bit further. However, if we apply the model to predict data in the other languages like Chinese or Arabic, we know that these languages are written in very different language script. The performance dropped significantly. And the reason is that we don't have enough label data in the other languages to train such a system. So motivated by these challenges, my goal is to extend the existing English-centric NLP methods across languages. And then I will mainly focus on how to generalize a pre-trained text representation across language boundaries and evaluate their performance on a set of NLP tasks. And then I will also go through some particular problems for cross-lingual learning of named entities. So in the first part, I will also introduce our cross-lingual evaluation benchmark to actually understand these multilingual representations. And in the second part and the third part, we will focus on named entities, and in particular, in the task of machine translation and dialog. So before we design any models or algorithms for cross-lingual learning, we know that we need to understand the research problem. How can we evaluate the performance of cross-lingual learning? And to understand these questions, we develop a cross-lingual generalization benchmark that has been used widely in research community. So first, as we take a look at our languages, we find that languages actually share similar word roots. For example, a word in English word significant might share similar word roots as a French word or a Spanish word. And also we find that languages share a considerable amount of underlying structures, such as word order or grammar. Some of the patterns might exist in both English, Chinese, or other languages like Tigrinya. And based on all these observations, many studies have proposed to train multilingual representations on more than 100 languages in a single model. And it also shows that sharing all the parameters across languages can help to transfer and help some low-resource languages. And the other advantage here is that we don't need to train 100 models for each language. Instead, we only need to train one single model. And then we need to just maintain one model. And this also simplifies a lot of pre-processing steps. However, as we also know that conceptually training a language model can be helpful to share knowledge across language, but there's still some key research problems. First, we don't know how this multilingual representations generalize across different tasks, and we don't know how this multilingual model generalize across different languages. More importantly, if we don't have a clear understanding of this model, we don't know how to design the next generation of multilingual models. So we introduced Extreme to help people understand this problem and interpret their machine learning models. We carefully select 4 categories of NLP tasks, which includes sentence classification, structure prediction, sentence retrieval, and question answering. And then we like to test on a set of representative languages from diverse language family and evaluate overall performance. And just to give a very brief review about pre-trained representations, usually we have some multi-layer neural network to encode the text, and then during training we randomly mask some tokens, and then we ask the model to predict the masked token given the unmasked context. And we can train these models multilingually so that we can use it to encode different languages. And for our work, we propose to evaluate the model by zero-shot evaluation. And by zero-shot, we mean that we have access to English label data for training, and then at test time, we directly apply the trained model to non-English unlabeled data to evaluate how well the model can transfer the knowledge learned from English to the other non-English data. And we select the test language based on two criteria. One is data availability and the other one is language diversity. So we end up have 14 language families and across over 40 languages. And let's see some discovery from our experiment. The y-axis here shows the normalized performance across different tasks, and the x-axis shows the different NLP tasks. Each dot in the column represents the performance for each language in a task. And first, we take a look at the first two columns, which are sentence classification. And we observe that the score across different languages are clustered in a small range. Well, if we take a look at a more complicated task like structure prediction, we find that the performance have a wider spread. And we find that because the model is still hard to actually transfer the structural information across languages. For example, some language might have different word orders, and it's hard for such multilingual models to actually recognize that. And we're also interested to know the performance across different language families. So the figure here shows the performance across different language family, and the y-axis is the normalized score. And each point here in each column represents the performance of a specific language family. So we know that if we take a look at some difficult languages like Chinese or Japanese, we find that the model is really it's really hard to transfer distant languages. For example, these languages are written in a completely different language script, and it's hard to transfer across this word form. And after we launched this work, we also attract a lot of participants to help develop the models and then push the performance a bit further. And we also receive a lot of feedback and keep improving the models and keep improving the analysis on our benchmark. So to summarize this part, we developed the extreme benchmark to actually provide the first step towards understanding a model's cross-lingual generalization performance. And we also launched an online platform for people to interact with their with this task and then actually observe their prediction behavior. And now that we have a good benchmark for multilingual models, I would like to shift our focus slightly to a very specific task called machine translation. And then later on, I will also focus on the other task called task-oriented dialogue. And in particular, we will focus on the cross-lingual learning of named entities. As we know that machine translation has become a key techniques to create multilingual training data by translating English data to the other languages. For example, the famous dataset XLM-R dataset is actually translated from English to 14 languages. And in this work, we focus on name entity translation because the proper translation of name entity is crucial, as many entities such as person, location names usually contain key information of the whole sentence. And they are also quite often low frequency words. Moreover, the translation errors of these entities will also affect the understanding of the whole sequence, resulting in misleading information. For example, the following English source sentence contains 3 locations, and if the model cannot correctly translate this location, the information will change. And in addition, we know that a lot of new entities are created every day. And these new entities might not exist in the parallel data traditionally used for training the machine translation system. Some entities like COVID-19 or metaverse and some medical terms might just happen, might be created every day. So to improve the quality of translating name entities, we propose a novel denoising-based pre-training method that utilize both multilingual text and the knowledge base. And we also propose a multitask fine-tuning strategy to mitigate the forgetting issue. And we will talk about this in the following slides in more details. And let's briefly review the denoising auto-encoding framework, which is a very popular pre-training objective for sequence-to-sequence model. And in denoising auto-encoding, we usually assume that we have access to a lot of monolingual text, and then we basically define a noise function and then add some noise to this monolingual text. And then we ask the model to reconstruct the original text from the noisy sentence. However, we know that there are several potential issues for this denoising auto-encoding procedure. First, the mask token or the mask band are chosen randomly. So some band might not contain key information. For example, the highlighted band in the document, such as of the 4 that is there, does not actually contain meaningful or complete information. And because the original text does not contain some translation information, it's also hard to actually utilize these models for downstream tasks like machine translation. But luckily, we have access to some open source knowledge base, such as Wikidata, that contains much detailed information about entities in a wide range of topics. For example, the entity like Modota, we can easily find its Wikidata page, which further includes its translation, its description, and other information like images as well. So we can potentially integrate such rich information to actually pre-train a machine translation model. Yeah, motivated by this observation, our work proposed a novel denoising entity pre-training method that integrates information from Wikidata with monolingual text. Specifically, our method first performed entity recognition on the monolingual text in the target language, and then we link them back to a knowledge base. Here we use Wikidata, and then we use a semantic parser called Slim to actually do the linking task. And then we replace the recognized entities by the translations in the source language. And then we add some noise to the code switch sentence as the denoising auto-encoding method does until we get sufficient code switch data. And then we optimize the model to reconstruct the original text based on the modified text here. So the advantage here is that we specifically encourage the model to predict name entities instead of arbitrary spent. And additionally, we also explicitly insert the translation supervision to the pre-training task. So we have code switch source sentence, and we ask the model to predict its translation. So by this construction, the model sort of understands the translation of some low frequency entities during pre-training. And the common practice for using pre-trained model is first like pre-train a model on monolingual data by a self-supervised objective, and then fine-tune it on parallel data with a machine translation objective. However, we also find that it's likely to forget some of the information that has been learned during pre-training if we fine-tune the model for many steps. So to address this forgetting issue, we investigate a multitask fine-tuning strategy that basically optimize the denoising prediction and the machine translation objective jointly during fine-tuning. And our model is trained with a mixture of denoising data and parallel data. So to distinguish the two tasks, we add the task embedding tokens. Here is denoted as empty or deep to help the model distinguish the input sentence. And we use Wikipedia articles on Russian, Ukrainian, and Nepali for pre-training and fine-tune the model on WMT dataset, tactile dataset, and forest dataset. And our models use a transformer model as a backbone, and we compare a baseline initialized randomly and fine-tune on machine translation objective. We also compare with two method, pre-trained method with deep and DAE objective, and then fine-tune with the MT objective. And the last two baseline are multitask fine-tuning baseline. Basically, we initialize the model with DAE or deep objective, and then during fine-tuning stage, we jointly optimize the pre-training objective and the MT objective. So we first evaluate this method by corpus-level matrices, such as BRU score or character F1 score. So we find that both denoising objective significantly improve over the random baseline in a single task setting. And our deep method can further improve the DAE methods in a multitask fine-tuning settings, especially for English to Russian translation. However, we also know that the corpus-level evaluation do not distinguish entity words and the other generic words. So this matrix might not be sufficient to show the subtlety of entity translation. So to investigate the performance on entity translation, we also perform the entity recognition on the test set and measure the entity translation accuracy. So we can find that multitask fine-tuning improve over single task fine-tuning in terms of word translation accuracy. And particularly, we find that multitask can also address the forgetting issue. And our deep method outperforms the DAE method in both single task and multitask settings. And to further analyze the translation accuracy for a different set of entities, we also do some fine-grained analysis. Specifically, we identify the entities appearing in 3 data sets. For example, the entities might appear only in the pre-training data set or fine-tuning data set or test set. So we categorize and denote this entity as PFT, which denotes the entities only appears commonly in the pre-training, fine-tuning, and test set. And similarly, PT denotes the entity only exists in pre-training and test set, or FT denotes these entities in the fine-tuning and test set. We can find that our method, which is the purple curve here, is the multitask deep method. And our method gets the highest accuracy score over different fine-tuning steps. And we also find that our score has better accuracy if we train them in a multitask setting. We also compare the accuracy gains over random baseline on entities grouped by the entity frequency, because we know that some of the entities are low frequency words and some of them are high frequency words. We would like to understand how effective our pre-training and fine-tuning can help improve those words based on different entity frequencies. So we find that compared with the DAE and deep method, our method can significantly improve the low frequency words. But we also have some forgetting issue. With the multitask fine-tuning, we can even improve the performance on this low frequency words and maintains the performance after fine-tuning. So to summarize this work, we propose a novel denoising entity pre-training method that performs entity recognition on monolingual text and entity linking to a knowledge base for entity translation. Then we propose an effective multitask fine-tuning strategy to prevent catastrophic forgetting issue. Our fine-grained analysis on 3 language pair shows the effectiveness of our method. Next, I will also introduce our recent work on multilingual TOD task-oriented dialogue research. So it's a very exciting NLP task recently get a lot of attention. as the globalization accelerates population mobility, there is a huge demand on information search. For example, like language translation, communication, and based on these reasons, virtual assistants provides a natural language interface to help people accomplish a wide range of tasks, such as ordering tickets, booking hotel, navigation to maybe a location, and all this convenient natural language interface can be more helpful if we can generalize this to the other languages. And let's also briefly review the overall pipeline of a task-oriented dialogue system. So let's see this figure. We have three components for a task-oriented dialogue system. The DST, or dialogue state tracking component, basically predicts the dialogue state from conversational history. And then policy optimization module basically retrieve information from a knowledge base and then predicts the next action. Finally, a response generation module will generate a natural language response based on the predicted action. And all these modules require annotations. However, as we know that many languages, we might not have a lot of annotators, and annotating all these labels might require a lot of efforts to train the annotator as well. So how can we utilize some existing data to generalize to the other languages? Traditionally, there are basically two ways to do this. And first, we can create some new data sets by asking people to annotate the data set from scratch. However, we know that this procedure is costly and time-consuming, while we can get very high-quality data. However, we also want to actually automate this process. For example, we can use machine translation to translate an existing English data set to the other languages, and then we can create this relatively cheap, and then we can also create large-scale data set. However, we know that some of these translation data set contain some translation artifacts. They basically ignore some local entities that are very important for a particular task like dialogue system. And then the model trained on such translation data set might overestimate the real performance in a more realistic setting. And in this work, we aim to generalize the task-oriented dialogue system across different languages for global users. Although prior efforts have used machine translation to translate English training data to other languages, as I mentioned, they simply translate all the entities in the target language, ignoring the fact that these translated entities do not actually exist in the target language location. For example, here, if I have an English dialogue and they mention some locations in London, if I translate this directly into Chinese, and if we deploy this system to help a Chinese user, we find that it will recommend some location in London rather than location in Shanghai. So this will create a localization issue where when we train the model, when we deploy this model to a target language location, we need to do some customization. And to address this issue, we collect a large set of local entities that exist in the target language location and propose a data-efficient framework to generate high-quality annotated data for training task-oriented dialogue system in 20 languages. So, and the other issue here is that the code switch scenario. For example, when bilingual users talk to people, code switch use cases are very common. For example, some bilingual user would tend to mix the entities in one language with the sentence context in the other language. For example, let's think about a case where a Chinese speaker travels to Dublin and asks a Chinese agent to actually recommend a bar. If a Chinese agent replies the local bar translated in Chinese, then the official translation actually never exists. And thus it's also not possible for the user to search this translation entity online if the user wants to find more information. And in this case, we'll rather use the original bar name in English as our response. So in this case, we'll create some code switch sentences as the generated output. So we also want to know that whether code switch is important in information search. So we also do a case study where we select 100 local entities in the original language and translated language. And then we search these entities online using Google search. And then we measure the failure rate of search results. And we find that if we use the translated entities to search the those information, we end up having a very high failure rate compared to searching their entity in their original language. So motivated by this, we can create a data set that basically consider 4 use cases. So E&E denotes a case where an English speaker traveling to an English-speaking location and then wants to search information. And FNF denotes a case where a foreign speaker traveling to a foreign language location and then communicates with the agent. And the other 2 are code switch use case where a foreign speaker traveling to an English-speaking location and asks for help. And similarly, ENF denotes English speaker traveling to a foreign language location. So our method can be used with local entities, and we propose data augmentation techniques to create this data set. So first, we assume that we have some English TOD data, so we can extract a template from this English data. And the templates look like this. For example, we identify the entities from the sentence, and then we replace those entities by some placeholder. And then after we extract such template, we translate the template with a placeholder into the other target languages. And then we collect a bunch of local entities, for example, in Chinese in this case, and then we mix the local entities with the translated template so that we can create a lot of the training data in 4 use cases. So this method has several advantages. First, it's easy to manipulate the entity. We can replace those entities in different languages so that we can create more realistic sentences that closely related to the local locations. And we can also just translate the templates rather than translate the whole sentences. And this helps us to create a lot of templates to bootstrap a lot more natural language conversations later. And we also have considered 2 settings. The first setting is zero-shot setting. We assume that we have access to an English TOD training data set and a machine translation system with some local entity. And the machine translation system can be used to create some translated TOD data for data augmentation. And the other setting is zero-shot setting, where we assume that we have additionally access to some post-edited TOD data in target language. So to just show you the concept here, for zero-shot, if we only use the English TOD data without any data augmentation, then we purely focus on zero-shot cross-lingual transfer setting. And if we have access to a machine translation system, we can directly apply this and then translate the English data into the other languages. And this is usually called as translated train. Well, if we have some local entity, we can use our pipeline to actually create some localized translated data. So we have the other data set for training. And all this method is done by the help of a machine translation system for data augmentation. And for few-shot setting, we have additionally access to the few-shot label data in the target language. And after training, we will evaluate the performance on the non-English test data. And as I show that we have different created data set, if we use the English TOD data without data augmentation, we can train the model for cross-lingual, pure zero-shot cross-lingual transfer. If we have the additional machine translated data, we can do data augmentation. So we can train the model on single use case. So we can have a SUC, which denotes a single use case model. And we can train the model with bilingual by use case. So we have another model. And then we can combine different data from different languages. So we can have multilingual by use cases. And moreover, we can combine all the data we have with multilingual and multi-use cases, so we can have a much larger training data sets. So let's take a look at the zero-shot experiment. We find that both zero-shot and translate train struggled in our benchmark, and it obtained less than 10 average accuracy in all the use cases. However, if we take a look at our method with data augmentation, we find that our data augmentation can help the model to improve the performance, especially on like zero-shot, over the zero-shot and translate train baseline. And we also know that the model, when trained on a lot of combination of all the languages and use cases, we can train a single model for all the use cases. We also want to actually try to estimate how well a translate trained model can perform in realistic setting. So we find that we create two test data, one test data with translated entity and the other test data with the real local entity. And we asked the translate train model to perform prediction on these two sets of test data. And we find that the translate train model performed really well on the translated test set, while it performed really bad on the data set with real local entities. This indicates a poor generalization performance to unseen real entities at test time. And we also want to actually benchmark the performance across different languages. So we asked, can we actually reduce the human post-editing efforts to create more data across languages? So we do some analysis where we have the machine translated data using local entities. And we also further ask some annotate professional translator to post-edit the test set. And then we perform some comparison for models on these two sets of test data. We find that the model perform quite consistent across these two sets of data. This indicates that actually with our automatic creation method, we can skip the human post-editing and obtain relatively high quality data for testing. So we can easily scale this method to 20 languages with the entities in the target language locations. So just to summarize this work, we propose a multilingual TOD dataset in 20 languages for 4 multilingual use cases, especially for code switch use cases. And we also propose an entity-based data augmentation method that we can help us to create a multilingual TOD dataset for training. And we also set up a public Libre board to actually help people to push forward this task. And finally, I would just like to conclude this talk by pointing out several directions to move beyond existing cross-lingual representation and the application. As we know that multilingual representations are really important to these multilingual applications. So some of the potential direction might include the tokenization method, where we also notice that nowadays people use subword tokens, but these subword tokens might change might be rigid and it cannot be updated across languages. So some of the techniques like byte-based model or character-based model might be very important. And the other one is language agnostic or language-specific modeling with some adapter model or model or parameter efficient learning method. And some of the other direction includes data augmentation or pseudo-labeling, especially for self-training method. The second thread of future research is based on evaluation of these multilingual models in generative tasks like dialogue generation or machine translation in low resource languages. And finally, I would also like to mention there is a urgent need to create multilingual data sets. So this can be some of the methods that we introduce in this work, like entity translation, is really helpful to create more realistic data set. And always there is a trade-off between the quality and the cost. And how can we develop methods to reduce the translation artifacts and balance the annotation course is an issue that we want to tackle. And also, I would like to point out that some of the data biases actually exist across different cultures. And especially when we tackle this multilingual task, we also need to analyze the cultural effects. And this is also really exciting. Okay, with that, I would finish my talk and open up for questions.
Well, thanks, Junjie, for this very exciting talk. And let's start with the questions in the chat. So there's one question from Kazem. So could you please elaborate more on the forgetting issue and how multitask fine-tuning could help with forgetting issue? For example, after fine-tuning, do we lose some of the weights or benefits of the underlying language model?
That's a good question. So let me try to clarify this by these slides. So if we compare like single task and multitask setting, which are highlighted in blue here. So single task means that when we do fine-tuning, we only do fine-tuning on the downstream data, which are the parallel data for machine translation, right? And for multitask training, fine-tuning, we fine-tune with additionally on the pre-training data set. And we can clearly find that the performance without the multitask setting, the low frequency word translation actually dropped significantly. However, with the multitask fine-tuning, basically, we still fine-tune the model with the pre-training task. So the model actually keep learning the translation of those low frequency entities. So the performance maintained after fine-tuning.
So in that case, I have another question. So in comparison to you treat the pre-training task as one part of the multitask learning, what if we don't do that, but we add a regularization between the pre-trained multilingual language model parameter versus the current parameter?
That's a good question. We didn't do that, but we assume that might be helpful to regularize the model prediction behavior, but still with many fine-tuning updates, the model might change quite a lot. So yeah, it's also interesting to investigate whether this regularization-based methods are more effective or not. My guess is that if we have like a more fine-tuning step, then the regularization-based method might work. While if we fine-tune the model for longer step, typically for machine translation system, we fine-tune the model for like 50 or 100,000 step, then this regularization method, the effect of the regularization method might decrease.
Yeah, because the multitask learning strategy sounds like we keep the model learning from the pre-training task, so it does not forget what it has learned in pre-training. But what if we just, use the pre-trained language model to distill itself?
Yeah.
Yeah, right. I mean, yeah, sure. So I think that's probably something we really don't know from this moment. So another question from Joe. So how are the entities extracted in the first place? Since the method is entity-centric, how much does it matter of the entity tagging system? I think that's regarding the second or the third.
Yeah, I think I can talk about both here. So for the first method, like we use a toolkit called Link, and Link is basically an entity linking toolkit where you can essentially they can use an entity recognizer to identify those entity and then link them to the Wikidata. So they have the entity recognizer by default. So this is one thing. For the dialog system, we also use the entity recognizer. So here we basically have the annotation in English. For example, for this task-oriented dialog data set, each sentence have their dialog state annotation. And this annotation actually identify the entities in the original sentence. So actually, we can naturally use those index to extract those entities. And in fact, in this one, I believe we don't have an entity extractor. Sorry.
Okay, thanks. Yeah, I have another question that's regarding your second work. So inside the DAE architecture, you have used the code switching data where you replace the entity to another multilingual counterpart, right? That's the way to create a code switching data. So let's say, what if, of course, code switching will always just replace the entity from one language to the other, but what if we use some kind of representation in the middle, which means that we can mix their embedding?
Yeah, that's a good idea. I think we haven't tried that. But the issue here is that for the multilingual model, when we do pre-training, the embedding for the other languages are randomly initialized. So so in that case, I don't know whether it will work at the very beginning when those embeddings are just randomly initialized.
Cool. Yeah. Thanks. So any other questions from the audience? Yeah, actually, out of curiosity, so regarding the cross-lingual forgetting issue, I wonder how you usually measure this effect. So
yeah, that's a good question. So in our work here, we particularly focus on translation accuracy. Basically, we do the annotation on the test set as well, and then measure how well the model translates those entities correctly. But it depends on the other application as well. And then I think forgetting issue is also important when the entity frequency are different. That's why we also do the analysis on different entities based on different frequency bind, because you also know that if those entity appears more frequent than the others, then the model might have a better chance to memorize them and then learn it better. So it's also great that we can have more fine-grained analysis across different binds. And also for the entities, I also point out that some just appeared in the training set, some appears in the fine-tuning set, and those unseen entities are also important. So if we have access to like external Wikidata knowledge base, probably we can access very complete or relatively complete entity sets. So we can also measure how well the model relies on this external information rather than memorize the entities in the training data.
Cool, thanks. Yeah. Yeah, also at the end of basically the last slide, which you talked about the future work. Okay, I'm actually wondering this. So can you give an example of, let's say, what is the typical kind of translation artifact?
Oh yeah, that's a good point here. So for translation artifact, you can see in our example here, maybe let me show you this figure. So we have two test sets. One is translated test set, which is usually the way people create multilingual benchmark. They just translate all the sentence blindly without actually recognize the entity. And in this case, you can use translation makes a lot of mistakes, especially for entities. So it's really easy for the model to actually predict that entity, right, as the dialog dialog tracking task. But if we replace those entities with real local entities with correct spelling, with correct the location names, and then the model's performance drops significantly. So for example, the model might just pick up the pattern of misspelling or like translation errors to actually identify those entities rather than actually understand the sentence to pick up the correct entity. So we know shows this figure that if we use this translated method to create the test set, we introduce translation artifacts, and this leads to overestimation of the trained model.
I see. This sounds really relevant to the BrewDog example.
Yeah.
Because that example can be viewed as the model is just blindly reading the surface form of this entity itself instead of really, contextualizing it in the entire context.
Yes, exactly.
Okay. Yeah, that makes sense. Cool. Any other questions from the audience? Although we are already reaching the end of the seminar. Yeah. I guess we can conclude the seminar for now, and we'll have more discussions in the one-on-one meetings.
Sounds
cool.
Good.
Yeah, thanks very much for Professor Hu again for this very exciting talk.